so this is Unit 4, Multiple Integrals, Section 15.4, Applications of Double Integrals, and we're going to start with density and mass. So as you may have seen in your physics classes, we can use single integrals to calculate moments of and the center of mass of thin plates, or lamina as we call them, with constant density. But now that we have the double integral, we can consider something with variable density. So suppose that a lamina, or a plate, for lack of a better description, occupies a region D in the xy plane, and we're just going to define it as a circle. And its density in units of mass per unit area at a point xy is in this region is given by rho of xy, where rho is a continuous function on that region. This means that rho of xy is going to be the limit of my change in mass over my change in area, where delta M and delta A are the mass and area of a small rectangle that contains this point. So let's put a little bitty rectangle in here. And the limit is taken as the dimensions of the rectangle approach 0. So to find the total mass, we're going to divide this rectangle R containing this region into subrectangles, and just like we did with Riemann sums, and we're going to end up with that our mass is going to be equivalent to 1 to k, and your sum from j equals 1 to L of rho of each of these points, which you should recognize as the double Riemann sum formula. Now, if we increase the number of subrectangles, we then obtain the total mass as the limiting value. So we end up with that the mass is the limit as k and L approach infinity, which then gives us the double integral over the region D of our density function, rho of xy, dA. So physicists have also considered other types of density that can be treated in the same manner. So, for example, if an electric charge is distributed over a region D and a charge density, given in units of charge per unit area, is given by sigma of xy, then the total charge on that plate or region is given by the integral in equation 2. So let's go ahead and take a look at example 1. We have a charge distributed over the triangular region D in figure 3, so that the charge density is given by sigma of xy is equal to xy. And that's measured in coulombs per square meter, and we want to find the total charge. So we know that our total charge is going to be the double integral over the region D of sigma of xy dA. So we need to set up our double integral, and we know that we're going to integrate xy. And in this case, I'm going to integrate with respect to y first, and then x. And I'm choosing that because this is my functions are in y. So I'm going to integrate from 1 minus x to 1, and my x values are going to be from 0 to 1. From there, going through the integration, we're going to end up with 5 over 24 coulombs, and that would be the total charge. So we can also use double integrals to find moments and centers of mass. So we can find that the center of mass of a lamina with constant density, and here we're going to consider a lamina or a region with variable density. So again, we're going to sketch this. So we're going to suppose that some region D occupies a region D and has a density function of rho of xy. So we have that the moment of a particle about an axis is the product of its mass and its directed distance from the axis. So again, we can divide into small rectangles and we end up, so let's go ahead and do a representative rectangle. And we know that the mass of that rectangle is going to be approximately rho of the point, Yij, times the area. And so we can approximate the moment of that with respect to the x-axis by multiplying by the y distance. So, which then gives us the equation, sorry about that. Our moment in the x direction is going to then be our integral over the region D of y times rho of xy dA. Similarly, our moment in the y direction is going to be the double integral over the region D of x times rho of xy dA, where this is my x distance. So the physical significance of the center of mass is that the lamina will behave physically as if the entire mass is concentrated at its center of mass. That's where rotation happens. That's where movement happens, and which you should remember from your physics. So what we have in figure 4 is that the lamina will balance horizontally when it's supported by the center of mass. And the coordinates x bar and y bar of the center of mass of the region, the lamina occupy region D, and with density function rho of xy, are given by these two equations, where x bar is our moment in the y direction divided by my mass, or 1 over the mass times the double integral of x rho of xy dA, and y bar is the moment in the x direction divided by the mass is equal to 1 over the mass times the double integral of y rho of xy dA. And then the mass is given by this integral. So if we look at the moment of inertia, which is also called the second moment of a particle of mass m about an axis, is defined to be mr squared, where r is the distance from the particle to the axis. We extend this concept to a lamina with density function rho of xy and occupying a region D. So again, let me go ahead and sketch that. And we know that the density is given by rho of xy. And here's my point. So, and again, we're going to divide the region into small rectangles, approximate the moment of inertia of each subrectangle about the x-axis, and take the limit of the sum as the number of subrectangles becomes large. And this result gives us the moment of inertia about the x-axis is then going to be the double integral over the region D of y squared rho xy dA, and our moment of inertia in the y direction, or about the y-axis, will give us x squared rho of xy dA. So it is also of interest to consider the moment of inertia about the origin, which is called the polar moment of inertia. And that's going to be the double integral over D. And in this case, that's going to be x squared plus y squared times rho of xy dA. And it is of note that the polar moment will be the moment about the x-axis plus the moment about the y-axis. Okay, so let's go ahead and take a look at example 4, where we're going to find the moments of inertia of a homogeneous disk D with density rho of xy is equal to rho, the center at the origin, and the radius A. So we're going to start with sketching the region. We know that it's a disk centered at the origin. So we have x squared plus y squared is equal to a squared. And in polar coordinates, we know then that d is going to be r theta, where r ranges from 0 to a, and theta from 0 to 2 pi. And so we know that then we have I0, or the moment about the origin, or the polar moment, is going to be my double integral from 0 to a and 0 to 2 pi of rho. And then we have, remember, x squared, so I'm going to write this x squared plus y squared. And again, we're trying to convert this to polar, so we end up with I naught, 0 to 2 pi, 0 to a, and this becomes rho r squared, and then r dr d theta. And lastly, because rho is a constant, we can pull it outside of the integral, so we have 0 to 2 pi, 0 to a, r cubed dr d theta. Okay, so continuing with the integration, we end up with that our polar moment is going to be pi rho a to the fourth over 2. Now, instead of computing our moment about the x-axis and a moment about the y-axis, we're going to use the facts that we know that I naught is equal to ix plus iy. And we also know that because the disk is homogeneous and it is a circle centered about the origin, we know also that our moment about the x-axis is going to be equal to the moment about the y-axis. And therefore, those are going to be equal to half of our polar moment, which means we have pi rho a to the fourth over 4. So notice that the mass of the disk in this problem is going to be the density times the area. So let me give myself some room. So mass, we know, is density times the area, which is going to be rho times pi a squared. And so the moment of the inertia of the disk about the origin can also then be written as, so I naught, which we know is pi rho a to the fourth over 2, is also going to be 1/2 rho pi a squared times a squared, which is then 1/2 our mass times the square of the radius. So if we increase the mass or the radius of the disk, we increase the moment of inertia. And in general, the moment of inertia plays much the same role in rotational motion that mass plays in linear motion. The moment of inertia of a wheel is what makes it difficult to start or stop the rotation of the wheel, just as the mass of the car is what makes it difficult to stop or start the motion of the car. Okay, previously you have learned about the normal distribution curve and have understood that this is a probability density function. Now, we know that from this that the f of x is going to be greater than or equal to 0 for all x, and that the integral from negative infinity to positive infinity of this function is equal to 1, and that the probability that x lies between a and b is found by integrating. So we have the probability that x lies between a and b is found by integrating from a to b of f of x dx. So now we're going to consider a pair of continuous random variables, x and y, such as things like the lifetime of two components of a machine or the height and weight of an adult female chosen at random. And so now we have the double integral. We have the joint density function of x and y is a function of f of two variables, such that the probability that xy, so probability that xy lies in our region D is given by the double integral over region D of f of xy dA. So in particular, if the region is a rectangle, then the probability that x lies between A and B and y lies between C and D can be given by this equation. So we have the probability that x is between A and B and y is between C and D is going to be my double integral from A to B and C to D of my probability density function dy dx. So because probabilities aren't negative and are measured on a scale from 0 to 1, we know that the joint density function has the following properties. We know that f of xy must be greater than or equal to 0, and we know that my double integral over the region must equal 1. The double integral over, and we're actually going to say this over 2 space, is equal to 1. The double integral over 2 space is going to be an improper integral defined from negative infinity to positive infinity and negative infinity to positive infinity of our probability density function. And we know that that must equal 1. So let's go ahead and take a look at an example of how to set one of these up. So we have the joint density function, f of xy is c times x plus 2y, if x is between 0 and 10 and y is between 0 and 10, and it's going to be 0 otherwise. And we want to find the value of the constant c, and then find the probability that x is less than 7 and y is greater than or equal to 2. Okay, so we're going to find the value of c by ensuring that the double integral of f is equal to 1. And because the function value is equal to 0 outside the rectangle, we have that our double integral from negative infinity to positive infinity and negative infinity to positive infinity of f of xy dy dx is going to be the integral from 0 to 10, and again, the integral from 0 to 10 of c times x plus 2y dy dx. So as we evaluate this integral, we're going to end up with that this integral we know has to equal 1, and we find that it equals 1500 times c. So we have 1 is equal to 1500 times c, which then gives us that c is equal to 1 over 1500. Now we can compute the probability that x is at most 7 and y is at least 2. So we have the probability that x is less than or equal to 7, and that should be a capital Y, is greater than or equal to 2 is going to be my integral from negative infinity to 7 and 2 to positive infinity of f of xy dy dx So we know that that is going to be, again, because of our defined area, it's going to be from 0 to 7 and 2 to 10 of 1 over 1500 times x plus 2y dy dx. And I will leave that calculation to you. And the solution to this will be the question in the video.